Testing? Testing? All right, C++, we're continuing in Chapter 6 on page 254 with the section 6.18, recursion. For some problems, it's useful to have functions call themselves. A recursive function is a function that calls itself either directly or indirectly. Just a special note, the main function should not be called within a program or recursively. C++ standard documentation indicates that main has its sole purpose to be the starting point for program execution. Recursion concepts. Recursive problem-solving approaches have a number of elements in common. A recursive function is called to solve a problem. A function knows how to solve only the simplest case, or sometimes called the base case. If the function is called with a base case, the function simply returns a result. If the function is called with a more complex problem, it typically divides the problem into two conceptual pieces. A piece the function knows how to solve, and a piece that it does not know how to solve. To make recursion feasible, the latter piece must resemble the original problem, but be a bit slightly more simpler or a smaller version. The new problem looks like the original, so the function calls a copy of itself to work on the smaller problem. This is referred to as a recursive call and is also known as a recursive step. Omitting the base case or writing the recursive call incorrectly so that it does not converge on the base case causes an infinite recursion error, likely causing a stack overflow error. The recursion step executes while the original call to the function is still open because it has not finished executing yet. The recursion step may result in many additional recursive calls. In order for recursion to eventually terminate, however, each time the function calls itself with a slightly simpler version of the original problem, this sequence of smaller and smaller problems must converge on the base case. At that point, the function recognizes the base case and returns the result to the previous copy of the function. And this sequence of returns ensues up the line until the original call eventually returns the final result to main. In the Chapter 6 lesson plan, please refer to the discussion of recursion. And I have a link in Chapter 6 lesson plan, so let's take a peek at that. Chapter 6 lesson plan, and in your read and do, it says section 6.8 recursion. Please refer to the following site for entertaining discussion of recursion. So let's go to that site. And how recursion works. Explains with flowcharts and a video. Be sure to watch the video too. And remember, this is your introduction to recursion. It is a very powerful and a very abstract topic. Again, common with mathematical problems and calculations, probability and statistics, but very fundamental to problem solving in computer science with its pros and cons. So experiment with this and try to understand as much that you can, and know that we're moving on to a new topic in Introduction to Fundamentals of Computer Science. So here the analogy is that we have a box and nested boxes within the main box, and each of those nested boxes packaged in the main box could actually have another box within them. This is interesting. In order to understand recursion, one must first understand recursion. And there's some narrative that continues. But in our recursive approach, understanding that in most cases, a recursion solution could be rewritten as an interactive solution. So iteration would be a while, a do while, a for, a repeat until, some type of iteration logic. But as we look at the iteration approach, even our flowchart looks a little more complex than does the recursive approach. And with a recursive approach, we're going to go through every item in a box. If you find another box, return and go through every item in the box. If you find another box, go and continue until you go through every item in the box and you find a key. Well, then you're done. We're looking for a lost key that's been placed in nested boxes. Well, there's more discussion, and I think they might be using JavaScript for the code. Just kind of overlook the syntax of the code. You can get the gist of the logic. And we have our C++ exact code, of course, in our textbook that mimics the logic that's being discussed here. So base case and recursive case. Something you have to look out for when writing a recursive function is an infinite loop. This is when the function keeps calling itself and never stops calling itself. And we would not want to write for that type of a model. We don't want that to happen. And if for some reason when you're designing your own code and using recursive functions and recursive calls on a PC device, it's Control Z to halt. An infinite loop, so Control Z. The call stack. I'm going to demonstrate the call stack for you a little bit later. Our function call stack, remember, it stacks the function call, retains the return address to the calling environment, and maintains its own local parameters and local variable contents until it's popped from the stack and all parameter and local variable values are returned for use by current memory, no longer available for our use. So our call stack will return to that in a little bit. Okay, I'm just scrolling down. There's more information. There is a video that you can play directly here or back in chapter 6. I ask you to refer to the video, so I'd like you to play that video and be sure to watch the video. Okay, I'm having troubles with my mouse. That's great. So you will have to, I guess, guide yourself through the video at chapter 6, and then be sure to watch the contents that I've indicated in chapter 6 lesson plan. Using my mouse pad right now. I'm not the most efficient with the mouse pad, so bear with me. Okay, an example of recursion is to create recursive program code to perform the popular mathematical calculation of factorial. Factorial on the bottom of page 254. Factorial is the result of a non-negative integer n as a product, and we write it as n factorial, where that's n with the exclamation point, and it's pronounced n factorial. And n factorial is the product of n, the number itself, times n minus 1, times n minus 2, times n minus 3. So n factorial, pronounced n factorial. We have a special symbol, the exclamation point, representing factorial. N factorial is equal to n times the number minus 1 times n minus 2 times n minus 3, and so on until we get to times 1. So, for example, 3 factorial is n times 3 minus 1 times 3 minus 2. So that's 3 factorial is equal to 3 times 3 minus 1 is 2 times 3 minus 2 is 1. So 3 factorial is itself times 2 times 3, which equals 6. How about 4 factorial? 4 factorial is the number itself times 3 times 2 times 1. 12 times 2 is 24. How about 5 factorial? That'd be n, 5 times 4 times 3 times 2 times 1. And that's 6 times 5 is 30 times 4 would be 120. Now we also want to look at our special cases where 1 factorial is equal to 1, and we define 0 factorial to be equal to 1 as well. A recursive definition of a factorial function is arrived at by observing the following algebraic relationship. So we can observe that n factorial is equal to n times n minus 1 factorial. Now let's just investigate this a little further. Algebraically, we're saying that n factorial is equal to n times n minus 1 factorial. For example, 5 factorial is equal to 5 times 5 minus 1 factorial, which is 5 factorial is equal to 5 times 4 factorial. Let's double check. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 5 factorial is equal to 5 times, well, 4 factorial would be 4 times 3 times 2 times 1. So sure enough, 5 factorial is equal to 5 times 4 factorial. I'd like you now to look at the next link I shared with you in Chapter 6, Lesson Plan. Which is the factorial discussion in detail. Now that link we explore from a mathematics perspective what factorial is. The factorial function symbol, the exclamation point, says to multiply a series of descending natural numbers. So 4 factorial is 4 times 3 times 2 times 1, 24. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5040. And then, of course, 1 factorial is equal to 1. And as we discussed, we define that 0 factorial is also equal to 1. Something you might notice is that we have 5 factorial is equal to 5 times 4 factorial. So to get 6 factorial, multiply 6 times multiply 6 by 120, which is 5 factorial. So 6 times 5 factorial. To get 7, we'd multiply 7 times 6 factorial, and so on. 10 factorial would be 10 times 9 factorial. And 10 factorial is actually equal to 3,628,800. Now let's just check that with my calculator. On your TI calculator, we're going to enter 10 and call the math key. Move over to probability. Slide down to option 4, which is your exclamation point. Enter. We have 10 factorial showing on the display. Enter to have it calculated, and we have 3,628,800. Now that keystroke again on your TI 83, 84, and 85 calculators. Type in your n value 10. Call your math functions. Slide across to the probability. Choose that and move down to option 4, which is your exclamation point, and enter to select it. And then enter to have 10 factorial calculated. So I'll try another one. Let's see, 7 factorial is 5040. 7, call your math key, slide over to probability, and then move down the list to option 4, which is your factorial. We have 7 factorial displayed on the screen. Enter to have that calculated as 5040. Just to give you an idea, we have a small list here of factorial numbers represented. 0 factorial, 1 factorial, 2 factorial, 3 factorial, we've kind of investigated those. 4 factorial and 5 factorial, we'll investigate those even further. And we know that 6 factorial is 6 times 5 factorial. 9 factorial is 9 times 8 factorial. We already know 8 factorial if we're going to be calculating 9 factorial, and so on. The point here is that using the function of factorial, your numbers get large very fast. And so we can easily surpass the internal calculation capabilities of your device. So with a function called stack, the factorial of any number is the number times the factorial of one smaller than that number. So in figure 623 or 25. Figure 625, a shared data file. You can go ahead and build your project at Visual Studio. Figure 625 on page 256. Now this is a .cpp, so it's a driver program. It's actually our program where we're going to be testing a recursive function called factorial. We have IOStream and IOmanip included, and we're using the namespace directive. In line 7, the unsigned long factorial function name, unsigned long is the function prototype, and unsigned long is discussed with you on page 257, where newer versions of C++ allow us to store even larger values with at least 8 bytes, that's 64 bits, to hold a positive integer. And of course, your range can get quite large. So the capacity of your device comes into play, and you want to be able to, again, with precision, extract the largest possible factorial value, and you will need to manage your data type in order to do that. Our system and our code on page 256 is using unsigned long and is stored in 4 bytes, 32 bits. And that allows us to store a positive integer in the range of 0 to at least 4,294,967,295. a long int. Remember there, a long int, we're looking at positive through the negative range, the range, the smallest negative number through the largest negative number with respect to a 4-byte capacity for assigned integers. So on our example on page 256, we're looking at unsigned long at this point. Our main function begins and ends. And looking closely, we have in line 18, unsigned long factorial, unsigned long number, begin, end, factorial. Now our base case, remember it's very important that we code a base case that each call to our function makes our function task a little bit simpler and does eventually converge to our base case. So if number is less than or equal to 1, the base case is executed in the true path and we return 1. Remember that our base case in this situation is 1 factorial equals 1 and 0 factorial equals 1. And then we end the true path of the if. If number is not less than or equal to 1, we process the else path, and we have our open close. So this is the end of the else or the false path. This is the recursive step. Else return our number times, and here's our recursive call, factorial, and we're sending number minus 1. Now, this is obviously simpler than the factorial of number. Factorial 5 calls factorial 4, and factorial 4 is simpler, easier to solve than is factorial 5. So, looking at factorial, we're passing an unsigned long integer value to number. If number is less than or equal to 1, we return 1. Otherwise, we return the number times factorial number minus 1. And we end and return our value to the calling environment. Recursive functions are sometimes use something called our function call stack, which we have talked about. When a function calls a function, that function goes on top of the call stack. This is similar to stacking books. You add things one at a time. Then when you're ready to take something off the stack, you always take off the top. Our code in our factorial discussion is very similar to ours, kind of stripped down a little bit. Function factorial of x, if x is equal to 1, equal 1, we'd return 1. Otherwise, we'd return x times factorial of x minus 1. Let's see if we can trace the function calls for factorial 3. If I call factorial 3, I'm going to push factorial 3 to the function call stack. It knows its return location, and factorial 3 has a local variable x assigned to 3. But we don't know how to calculate this yet. Factorial 3 needs to return 3 times factorial x minus 1. 3 minus 1 is 2, so we are calling factorial 2, and we'll push that on the top of the stack. Factorial 2 knows its return location. It's received an unsigned long int with a value of 2, so its local variable x is equal to 2. But it doesn't know how to solve this yet. it needs to return 2 times factorial 2 minus 1. 2 minus 1 is factorial 1. So we call and stack factorial 1 to the function call stack. It knows its own return location, and it's been passed a value of 1, so its local variable x is 1, and our code function factorial of 1. Well, if x equal 1, if it's equal to 1, we return 1. So we're going to return 1 to the calling environment and pop this function allocation record off of the top of the function call stack. We returned 1. 1 times x, well, x is 2. 2 times 1 is 2, so we're going to return 2 to the calling environment. We return 2 and pop factorial 2 off the top of this function call stack, returning 2. X is 3. 3 times 2 is 6, so we'll return 6 to the calling environment. And let's see, 3 factorial is 3 times 2 times 1. 3 times 2 is 6 times 1 is 6. So sure enough. Returning 6, and we pop function factorial 3 from the top of the function call stack. Here's another diagram of our function call stack, a little different perspective than what mine has been, but you will come across different drawings and different ways that we can try to visually show you what's happening on the function call stack. So in this case, we are looking at the factorial 3 being called and its processing block of code. So here's your allocation record. And we've got the line here and the line here. Factorial 3 is pushed to the top of the stack. We're working within factorial 3. If x equal 1, it doesn't, so nothing happens to the stack. Else, we return x times factorial 1 minus, or x minus 1, which would be calling factorial 2. So factorial 2 is pushed to the top of the stack, which moves factorial 3 down on the function call stack. With factorial 2, we're going to process if it equals 1. It does not, so the stack doesn't change. We're going to do the false path of factorial 2, which is return 2 times factorial 2 minus 1, which is factorial 1. Factorial 1 now is pushed to the top of the stack, and we have the allocation record for factorial where x equals 1, factorial where x equals 2, and factorial where x equals 3. Well, if x equals 1, equals 1, it does. We've called factorial 1, x locally equals 1, so we're going to return 1 and pop factorial 1 off the top of the stack. Returning 1, I have 1 times 2, which is 2, so I return 2 to the calling environment and pop factorial 2 off the top of the stack. And 2 times return 2, and then pop factorial 2 off the top of the stack. Returning 2, I have factorial returned 2. 2 times 3 is 6. I return 6, and factorial 3 is popped off the top of the stack, and no more of those local variables are known to our program. So a different visual, a different way to schematically represent the function call stack in a recursive program. And there are other schematics and drawings in mathematical journals as well as in computer science, but I hope with my little demonstration where I am trying to physically push and pop and then another schematic drawing that'll help you as you try to weave your way through some of those diagrams that might be presented to you in your future. Remember again, this is introductory. This is fundamentals. This is for most people the first programming course, and for those of you that have had Visual Basic, it's still your first introduction to object-oriented programming. So let's run our program and see what happens. Okay, so I have my student shared data file, figure 6_25. And I created my project. I made sure to set my pre-compiler settings accordingly and did a save all, so I'm ready to run. Control F5. And 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. We agree with that. 6 times 4 would be 24. 5 times 4 factorial would be 5 times 24, 120. 6 times 5 factorial would be 720, and so on. So according to our output from our program on page 256, we agree with the output at this point for 10 factorial. Now in the program itself, we have a for loop in main, allowing us to iterate from 0 to 10. And then we call factorial of 10, which sends as an unsigned long int 10 to number. We test locally if number is less than or equal to 10. It is not, so we call the recursive step return 10 times factorial. 10 minus 1 would be 9. And we're going to call that factorial function 0 through 10. Well, it's less than or equal to 10, so we'll actually call that function 11 times, 0 through 10. Well, we talked about our unsigned int and our unsigned long. So let's see if I change this to, instead of 10 times, let's try 25 times. So I'm going to generate factorial of 25. Control F5 and run. I gotta make sure that I get my code correct. And again, my mouse isn't working. Okay, factorial 0 through factorial 25 is executed. And we see that our numbers are growing rapidly. change to, let's try 30. Factorial of 30. Repeat 30 times, call factorial 30, and solve recursively. Notice it takes a little bit longer each time to solve. And we have our factorial 1 through factorial 30. Again, our numbers are growing. Maybe we could try factorial 40. We're testing the capacity of unsigned int. How large can our numbers get? Control F5 to execute. Seems to take a bit longer to execute and process, and we're, factorial 33. In fact, look at and compare factorial 32 and 33. They're both the same, so we're losing some accuracy here as we approach these larger values. So factorial 30, we need to double check that to see if that's accurate on some other device. But we're reaching the internal capacity for storing an unsigned int on our system. So let's try an unsigned long, which is C++11 version. I'm changing the protocol to an unsigned long, and changing the function signature to unsigned long. And this is on page 257, your C++ type unsigned long int, and a discussion that would enable us with type assignment of unsigned long int to store values in at least 8 bytes. That's 64 bits, which could hold numbers as large as a large number on page 257. So let's see what we get when we try unsigned long. So F5 to calculate, taking a bit longer to process. And it looks like we have accuracy through 40 factorial. Let's reset and try through 75 factorial. Changing my counter, I'll be calling factorial 75 recursively. Let's control F5 to execute. Takes a bit longer to process and execute, and okay, it looks like we're losing our accuracy somewhere around factorial 64 and factorial 65. We'd want to double check on some other accurate device to make sure we are accurate through some point. But again, even with an unsigned long and C++11 conventions being able to store very, very large integer values, so we're losing accuracy rather soon with this factorial function. So a couple things you can do with your student there. Shared file figure 625 is to run it a couple times, checking to see where that largest unsigned long occurs, and then change your data types to unsigned long in the prototype and then also in the function definition, and run again and see where that largest capacity is on your device for calculating a n factorial recursively C++ programming code. Now on page 660, there's a discussion about recursive or iteration. Remember, iteration is using repetition. Iteration is using repetition, like our while do, our do while, our repeat until. Some of these iterations that we have a variety of methods to repeat until something occurs or repeat while true, depending on the language that we're using. But iteration is the fundamental logic. Most recursive functions can be implemented with iteration. But these are some things we should be concerned about. Both iteration and recursive are based on a control statement. Iteration uses an iteration statement like, while true, we're going to continue to process, but when false, we exit. Recursion uses a selection statement. If this is the base case, we will return. Both iteration and recursion involve iteration. Iteration explicitly uses the iteration statement, while, repeat until, do while. Recursion achieves iteration through repeated function calls. Iteration and recursion each involve a termination test. Iteration terminates the loop when the loop condition fails. Recursion terminates when a base case is recognized. Counter control iteration and recursion each gradually approach termination. Iteration modifies the counter until the counter assumes a value that makes the loop iteration test false. Recursion produces simpler versions of the original problem until the base case is reached. Both iteration and recursion can occur infinitely. An infinite loop occurs with iteration if the loop continuation test never tests false, and infinite recursion occurs if the recursion step does not reduce the problem during each recursive call in a manner that eventually converges onto our base case. We are at the wrap-up section of Chapter 6. Please return to D2L, the overview document. For Unit 6 is where we've been working. To check for your homework projects, tests, due dates, and all details, there's several videos to watch now and listed in your lesson plan associated with this video of my recorded lecture, and multiple lecture recordings in this chapter covering the many topics that were introduced, again, in an introductory way. So again, congratulations. We're working through fundamentals of computer programming. Thank you very much.